Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 1 for this week. And the more I went through the production of this, the more I realized that I probably bit off a little bit more than I could chew in terms of actually being able to explain everything that goes in to manually calculating the sunrise and sunset times. But I have included the basics here, and I'll try to make some sense out of it for you. But there are an awful lot of factors that go into this. So let's go on ahead and get started. So here are some numbers to start with. The Earth rotates 360 degrees in one day. Well, not exactly. Okay, it turns out the Earth makes one complete turn in 23 hours and 56 minutes. But for the purposes of this argument, we'll keep it simple and say that it goes 360 in one day. And it takes 24 hours to do this. Well, based on what I just said with point number 1, that's not exactly true, but it's close. Now, if you divide 360 degrees by 24 hours, then you get 15 degrees per hour. So the Earth is rotating at about 15 degrees longitude per hour, and that adds up to 360 at the end of the day. And since the Earth's axis is tilted, latitude becomes very, very important. For instance, on the first day of summer, when the North Pole is pointed toward the sun, then the days are longer. In fact, it's 24 hours continuous daylight up there. And then the days actually get shorter as you head south toward the equator. And then at the other time of year, where the South Pole is pointed toward the sun and the North Pole is directed away from it, then the days actually get, make sure I'm stating this correctly, the days actually get shorter as you go north, okay? And so, in fact, there's continuous darkness at the North Pole, for a couple of months during the winter. So that obviously has a huge impact on the sunrise and sunset times. Now, the sun's declination angle is the angle at which the sun is with respect to the equator. Where is it directly overhead? And those numbers range from plus 23.5 degrees latitude to minus 23.5 degrees latitude. The 23.5 plus is on June 21st, and the other one is on December 21st, or thereabouts. And RDU's latitude and longitude are 35.8801 north latitude and minus 78.7880 longitude, respectively. Okay, so here are the sun's farthest north and south positions. There is the equator. And again, it gets as far north as 23.5 north in the summertime, June 21st, and minus 23.5 on December 21st. And we are sitting at 35.8801. So the sun never gets directly overhead at RDU, but it comes within about 12 or 13 degrees of doing that. And then when it's down in this position, down at minus 23.5, then it's very low in the sky compared to what it is in the summertime, only about 30 degrees above the horizon. Now, and there's the RDU longitude, and for the purposes of this argument, we'll put it right in the middle there at minus 78.7880. Okay, so here's a little trigonometry for those of you that took this and may remember it. If you don't, and you just don't care about this, you're not going to hurt my feelings. This is just some interesting tidbits for those that are interested. Now, here is what I'm going to call this a unit circle. The radius of this circle is 1 from the middle to the outer edges all the way around. Now, we're going to split this up so that on the right-hand side there, we're going to say this is 0 degrees or 360, depending on how you want to view it. And then 90 degrees at the top, 180 on the left, and 270 down at the bottom. Now, in trigonometry, there's something called radians, and it turns out that 360 degrees is equal to 2 pi radians, and pi is 3.14 and a whole bunch of numbers after that, okay? So 2 pi is about 6.28 with a whole bunch of numbers coming after that. And so the equivalent here is 0 degrees or 360 degrees is equal to either 0 or 2 pi radians. 90 degrees is pi over 2 radians, 180 is pi, 270 is 3 pi over 2, and then you're back to 360, which is 2 pi. So that's just the basic nuts and bolts of trig. Now, if you take that same unit circle and you draw a line at a 45-degree angle to the horizontal line there, and then bring that straight back down to that horizontal line, then you have a 45-degree angle in this case, and this is what we call a right triangle, where we have a 90-degree angle there between the vertical line and the horizontal line. So the sine of an angle is defined as the length of the opposite side compared to the hypotenuse. Now, what the heck is the hypotenuse? The hypotenuse is the side that is opposite the 90-degree angle, okay? So that would be that line that's going up at a 45-degree angle there. And so it would be the ratio of that opposite side to where the 45-degree angle is to the hypotenuse, and the cosine is the length of the adjacent side compared to the hypotenuse. So that's how you come up with those numbers. And in this case, when the angle is 45 degrees, both the sine and the cosine turn out to be 0.71. And that sort of makes sense, because if the length of that line that's at the angle there is 1, you can see that both the opposite side and the adjacent side are less than that, okay? So 0.71 makes sense. Okay, so now we get into some calculations, and it's way beyond the scope of this video to get into why these equations have the terms that they do, but we'll simply fill in the blanks here. So the sunrise is equal to that long equation there. Now, the reason it starts off with 12 is that solar noon is going to be 12 hours, okay? And then we talked about the fact that every hour is 15 degrees, so that's where the 1/15 comes from. Now, what the heck is an arc cosine, okay? Well, if you take the cosine of an angle, you get a number. If you want to work backwards from a number to get an angle, then you do the arc cosine, okay? So when you plug in all of those numbers, you put in our latitude and the declination angle of the sun, then you get 6.1608, which is 6 hours and 10 minutes. And for daylight saving time, that would turn out to be 7:10 a.m. You add an hour. For sunset, the only difference is we add the 1/15 instead of subtracting it. And when we plug in those numbers, then we get 17.8392, which is 17 hours and 50 minutes. And you add 1 hour to that, and you get 6:50 p.m., okay? And finally, the exact actual sunrise and sunset times are slightly different for a number of reasons. Number one, we have an atmosphere, which actually bends the Earth's rays toward us before the sun actually is visible. So we see light before the sun is there, and we see it after the sun is there, okay? And so as a result, that lengthens the day a little bit. That's why the sunrise and sunset are not the same in terms of numbers on the equinox, because we're getting some bonus light because of the atmosphere bending the sun's rays. The other thing is that the Earth is tilted, okay? We all know that, so that plays into it. And then finally, the Earth's orbit around the sun is elliptical. We're actually closer to the sun in January than we are in July, and so we rotate faster during the winter months than we do during the summer months. And so the Earth-Sun time system is not like ours, where every day is the same, okay? The length of a solar day actually varies, okay, because of the fact that the Earth is rotating at quicker or at different speeds around the sun, depending on how close it is to the sun and what time of year it is. So, all right, well, I hope that made at least a little bit of sense. It's just sort of an interesting exercise to go through. Of course, you can go online and plug in your latitude, longitude of your city and get the sunrise and sunset without going through all of this. But for those of you that are mildly interested in how those numbers come about, this is about the best I can do on that. So, all right, folks, that is it for today. That's bonus weather video number 1. And hope you have a good rest of your Monday evening if you're still up and around. And if you're not, hope you check this out tomorrow, and we will see you again tomorrow with the next daily weather update, next bonus weather video coming up Wednesday. You all take care, folks, and we'll talk to you soon.